Hello, class. Sorry I'm a bit late. I was brushing my teeth, and I guess I brushed my teeth for longer than I realized I do. Um, so, today we are going to talk about a concept that has a couple of different names. Okay, so the one that I'm going to use is rotational inertia. Um, so, that's the topic of today's lesson. It is also known as moment of inertia. Or also sometimes just known as inertia. Okay, so I'm going to use rotational inertia, but you might, if you want to learn more about this topic and you look it up online, you might also try searching some of these terms. Um, so moment of inertia is a measure of how difficult it is to start / stop rotation of an object. Okay, and I say the difficulty to start or stop the rotation of the object, and I mean that in the absence of friction. So, if we think about an object, if it's rotating about some axis, typically there's going to be some friction between the object and the axle that it's rotating about. Which is why you would, lubricate the axis of rotation somehow. But we're not talking about the friction, because friction makes it more difficult to start the rotation of the object. So an important point about inertia is that it is only defined, inertia is only defined for so-called rigid bodies. So when I say rigid bodies, I mean objects that aren't flexing very much. So this calculator is a rigid body. It doesn't want to bend. Okay. This stack of Post-it notes is not really a rigid body, so it flexes. Okay. So you wouldn't define rotational inertia, for example, for a liquid, because liquids can slosh around and change shapes. They're definitely not rigid. Okay? It depends on, so what does the rotational inertia depend on? It depends on two things: the amount of mass, okay? And it also depends on the distribution of the mass about the axis of rotation. Okay, and that's an important point. It depends on the distribution of mass about the axis of rotation. So what do I mean by that? Well, I have my baseball bat here. Okay, here's my baseball bat. And one of the things you'll notice about a baseball bat is it is not uniform. Okay, the baseball bat is thicker at the end so that it is a bigger target for the baseball to hit. and it's thin at the handle. Okay? So if I'm swinging the baseball bat back and forth, the axis of rotation is at my hands. Okay? So this mass is distributed about the axis of rotation. Now, it's pretty difficult to swing this baseball bat. It's a heavy wooden bat. Okay? But if I change the axis of rotation, then the rotational inertia changes. Okay? So what if I flip the bat so that the handle is now far away from my hands, and I swing it like this? This is super easy to swing back and forth. Okay? Why is that? It's because if I hold the bat like this, most of the mass is close to my hands, so it's close to the axis of rotation. Okay? That makes it easier to swing. If I flip the bat around, now most of the mass is at the end, which is far away from the axis of rotation, so that makes it more difficult to swing. Okay? If you're playing baseball, the pitcher throws the ball at you and you have to swing and hit it. If you're too slow, it's another way of thinking about it's too slow. If you're too slow and you miss the ball because you were too slow, then that means it was too difficult for you to start the rotation of the bat. Okay? So in other words, the rotational inertia of the bat was too great for you. So one of the things that your coach might yell at you to do is they might yell at you to choke up, which means you now hold the bat further up. And when you do that, now this is an extreme version of choking up. You might only choke up like this much or something. But when you choke up, you're moving the mass closer to the pivot point, to the axis of rotation, which makes it easier to swing. It reduces the rotational inertia. And so now you can swing just a little bit faster and maybe hit the ball. Okay? So swinging a baseball bat is related to rotational inertia. So I have not given you a formula for rotational inertia. So let me give you a mathematical formula. So let's suppose you have a mass m, and it's moving in a circle. Okay. Here's the center of the circle right here or so. And the radius of that circle is r. Then the rotational inertia of this mass is going to be the size of the mass times r squared. So this is the inertia of a single mass. Okay? That's the inertia of a single mass. All right, and what we can see is what if that mass is going in a bigger circle, for example, out here? Then it has a larger radius, okay? It has a larger radius, and for that reason, it's going to have a bigger inertia. So this explains my comment about the bat, okay? If I'm holding the bat like this, then this mass is far away from the pivot point, which is my hands, okay? If I hold the bat like this, the mass is close to the pivot point. It has a small r, so it's a smaller inertia. It's easier to twist the bat, okay? So this is our main formula for today, which we are going to be playing around with. If you have a system consisting of multiple masses, then the inertia is just going to be the sum of mr squared for all of them. So you do mr squared plus mr squared plus mr squared, etc. Okay? It's pretty easy from this formula to deduce the units of inertia. The units of inertia are going to be units of mass times units of distance squared. So they're going to be kilogram meters squared are the units of rotational inertia. Okay? So we're basically just going to do one example today, but it's kind of a long example. So here's our example. Let's consider a system of 4 masses in a square. So you have 4 masses in a square configuration. So let me draw this system. I'm going to draw it fairly big. All right, so there's my square. And in each corner of the square, there's a mass. Okay, so the mass right here is 3 kilograms. The mass right here is 2 kilograms. The mass right here is 4 kilograms. And the mass right here is 1 kilogram. Okay? Now remember, inertia is only defined for rigid bodies. So these 4 masses are connected by some kind of a frame, okay, that holds them together into a square shape rigidly. Okay? And the side length of the square is 5 meters. Okay? So what we're going to imagine is rotating this square about a number of different axes. So I'm going to define the axes of rotation. So the first axis of rotation is, I'm going to call it axis A. And it's rotating it about that axis. The second axis of rotation is actually out of the page, and it's rotating it about the lower left corner. So I will call that axis B. The third axis of rotation is rotating about a vertical axis about the left side of the square. So that's axis C. The third axis is another axis that is out of the page, and it's about the center of the square, which I'll call axis D. And then the last axis of rotation is along a diagonal of the square. So rotating it like that, I will call that axis E. Okay, so let me show you what each of these types of rotations means. Okay, so let's suppose this sticky note is the square. Okay, rotating it about axis A, that's an axis that is, through the center of the square. Okay, so that would be like rotating it like so. Okay, that's axis A. Axis B is rotating it about a corner of the square, and the axis is out of the page, so that's rotating it like this. Okay. Axis C is rotating it about the left side of the square, so it's kind of like opening a book. Okay, opening the cover of a book. Axis D is rotation about an axis through the center. So that's kind of like this. like that. And then lastly, axis E is rotating it about an axis that goes across the corners, okay? Like that. Okay, so these are the different axes of rotation. Now I want to talk about squares for a second, just so we understand the geometry of squares. So if you have a square that is 5 meters on a side, then the diagonal of the square you would get from the Pythagorean theorem. So it would be square root of 5 squared plus 5 squared from the Pythagorean theorem, which is the square root of 50, which is 5 square root of 2. So this diagonal has a length of 5 square root of 2. Okay? What if we wanted to know what is the distance from the center to a corner of a square? That is going to be half of a diagonal. So that would be 5 root 2 over 2, which is 5 over root 2. So full diagonal is 5 root 2, half a diagonal is 5 over root 2. And then also, of course, if we have half of a side length, so not a full side length, but half of a side length, that would be 2.5 meters. So we have 2.5 meters and 2.5 meters. Okay, so that's just a little bit about sort of the geometry of a square of side length 5 meters. The reason I'm going over that is because the rotational inertia is mr squared. So we have these distances that we need to calculate. So I'm just bringing that up. Okay. So axis A, we're going to calculate the inertia of axis A, about axis A. All right. How far is this 2 kilogram mass from that axis? Type it into the chat if you know the answer. Furthermore, how far away is the 3 kilogram mass from the axis of rotation? And how far away is the 1 kilogram mass from the axis of rotation? And the 4 kilogram? I'll give you a hint. It's the same answer for them all. I'm waiting. 2.5, thank you. So the entire side length is 5, and I can see that each of these masses is half a side length away from the axis of rotation. Okay, so all 4 of the masses are 2.5 meters away from the axis of rotation. So I do mr squared for each of them. So for this one, it would be 2 times 2.5 squared. For this one, it would be 3 times 2.5 squared. For this one, it would be 1 times 2.5 squared. For this one, it would be 4 times 2.5 squared. All right? So if I work that out with my calculator, I get 62.5 kilogram meters squared. Okay. Now let's think about axis B. Type it into the chat if you know how far is the 1 kilogram mass away from the axis of rotation. Excellent. The 1 kilogram mass is on the axis of rotation B. All right? So what that means is that its distance is 0. All right? So an important point is anytime a mass is on the axis of rotation, okay, anytime a mass is on the axis of rotation, it has r equals 0, and therefore it has I equals 0. All right? But there are other masses, so we have to calculate for the other masses as well. How far is the 3 kilogram mass from axis B? Well, here's the axis of rotation right here, for example. I'm rotating it like this. I can see that this corner of the square is a full side length away. So it is 5 meters away. So I have 3 times 5 squared. Similarly for the 4 kilogram mass, okay, I'm rotating it like this. This lower right-hand corner is a full 5 meters away. So I have plus 4 times 5 squared. And then lastly, I have the 2 kilogram mass, which is on the opposite side. So we can see that it's a full diagonal away. All right. So I have 4 times, 2. It's a 2 kilogram mass. My bad. And then the full diagonal of the square, we said, was 5 root 2 from the Pythagorean theorem. So we have 5 square root of 2, quantity squared. So let me work this out. And we get 275 kilogram meters squared. So we can see that about axis B, all right, for axis B, we can see that it's much larger rotational inertia than axis A. So that means you would have a much harder time rotating the square around axis B than you would about axis A. All right. So let's do axis C. What is the rotational inertia about axis C? Who can tell me which masses are not going to contribute to the rotational inertia of axis C? Type it in the chat. Exactly. So the 1 kilogram and the 3 kilogram are both on the axis of rotation. So we're only going to get contributions from the 2 kilogram and the 4 kilogram. So we have 2 times something squared plus 4 times something squared. Okay. So how far are these masses from the axis of rotation? Well, here's the axis of rotation along the left side of the square. This lower corner is 5 meters away from that axis, and so is this upper corner, also 5 meters away. Okay? So they're both 5 meters away. 6, 7, 25. That's 150 kilogram meters squared is the inertia. Axis D. All 4 corners of the square are the same distance away from the center. Okay? And that distance is half of a diagonal. So as I mentioned before, half of the diagonal of this square is 5 over square root of 2. Okay? So I'm going to have, so this distance is 5 square root of 2. So I have 3 times 5 over square root of 2, my bad. Plus 2 times 5 over square root of 2 squared. Plus 4 times 5 over square root of 2 squared plus 1 times 5 over square root of 2 squared. So crunching the numbers on that, we get 125 kilogram meters squared. So there's some questions in the chat. Okay. How do we get 5 over square root of 2? Okay, so a full diagonal, so this is a square of side length 5 meters. So according to the Pythagorean theorem, an entire diagonal would be 5 times square root of 2. Because you do the Pythagorean theorem, you get square root of 50 is this length, which is 5 square root of 2. Okay? The distance from the center to the corner, we can see is half of a diagonal because we have a diagonal on each side. Okay? So from the center to a corner is 5 square root of 2, half of that. Now square root of 2 over 2 is 1 over square root of 2. So that's why I wrote it as 5 divided by square root of 2. All 4 masses are the same distance from the, all 4 corners of a square are the same distance from the center. That's why it's the center. Okay? So this is 5 over square root of 2. This distance is 5 over square root of 2. This distance is 5 over square root of 2. It's all 5 over square root of 2. Okay? So I hope that makes a little more sense. For axis E, axis E is the one that's rotating about the diagonal. So who can tell me which mass or masses are not going to contribute to the rotational inertia for axis? So correct, the 1 kilogram mass and the 2 kilogram mass are on the axis of rotation, so they won't matter. Okay, so we're only going to have terms for the 3 kilogram mass and the 4 kilogram mass. All right. Now, how far is the 3 kilogram mass from that axis of rotation? Well, it's that far away. So we can see it's half a diagonal away. Same thing with the 4 kilogram mass, half a diagonal away. So both of these are 5 over root 2 away. And contributing 7 2 times 87.5 kilogram meters squared is the inertia about that axis. So it's the main lesson here is that it is more difficult to rotate something about certain axes than other axes. Okay, so I have a question. Type it into the chat if you know which axis is the second most difficult to rotate about? I typed it into the chat. Which axis is the second most difficult to rotate about? And that's kind of a complicated question, so I typed it. So if you know the answer, put it into the put it in the chat. I need to move something into the dryer, so give me 1 second.
Awesome. Hello, awesome.
All right. Second most difficult is axis C, correct. So you can sort of rank the difficulty just going from biggest number to smallest number. Very good. All right. Sometimes, so this is an example of an object that is made up out of discrete masses, okay? Sometimes you have objects that are not made up out of a bunch of discrete masses where you can say, there's mass 1, there's mass 2, there's mass 3. Like, what if you wanted to calculate the inertia of a coffee cup, for example? Or what if you wanted to calculate the inertia of this? You know, it's not made up out of a countable number of masses, okay? So in that case, so I'm going to call those odd shapes. So odd shapes have inertias, have inertias that are calculated using methods from calculus. Okay, now this is not a calculus-based course, but we will have occasion to use some of these shapes. And so what happens on the IB exam is they just give you the formula for the rotational inertia, okay? So I'm going to give you some of those because you won't be using it in today's quiz, but you will be using it in some of the later ones later on this semester. So the first one is a solid disk. So here's a solid disk. Its axis of rotation is through its center, like that. And I will shade it in to indicate that it's solid. A solid disk has an inertia of 1/2 mass times the radius squared. Okay. What if you had a solid sphere, like the Earth? Okay. And you rotate it about its center. that, and I'll shade it in to indicate that it's solid. So that's like the Earth. It has an inertia of 2/5 mr squared. Okay. What if you have a hollow sphere? A hollow sphere. So a hollow sphere would be like a ping pong ball. All right. A hollow sphere has an inertia of 2/3 mr squared. So we're going to be using these equations for inertias of weird shapes later on in the class. You won't need it for today's quiz, but go ahead and write those down. Okay. At any rate, that is my lesson for today, and I will be seeing you in the Zoom room in just a moment.